radium waves which are picked up by the radio get good transmission.
There's altimeter, which is used in aircraft and beams radiation down, and the speed at which it comes back up is used in the equation to work out how high it is.
There is a seizures, and they can be X-rays can be used to find out if they've got any diseases and sometimes cure them.
Infrared radiation, which is used in cooking and heating.
Alarms, which is also used is infrared, and if anybody walks in the beam, then it sets the alarm off.
Television, which uses radiation beams to transmit images to the screen.
Infrared photos, which use photo to get clear pictures for agriculture and medical uses.
Optics is like looking at light and radiation on the electromagnetic spectrum.
And natural radiation, which is used for scientific purposes and but can sometimes be bad.
Our talk is on useful ways in which radiation is used. It comes in many forms. Forms of radiation are gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves and radio waves. They all have different wavelengths. All of these forms of radiation are part of the electromagnetic spectrum. Gamma rays are very much the same as X-rays. X-rays are used to see through people and animals to see the bone structure, but too many X-rays can be harmful. Ultraviolet light is used on sunbeds to get tans. Visible light comes in many forms, from fire to light from light bulbs, although with very small amounts of infrared and with very small amounts of radiation. Infrared radiation is used for cooking. Microwaves are used for microwave cooking. Radio waves, which have a wavelength of 1 kilometre, are used mostly for radio and television signals. Not all radiation is harmful. One of these non-harmful forms of radiation is visible light, another is radio waves.
One use of radiation is in microwaves, because they use infrared radioactive waves, and they go inside the food and heat up to the inside, so it's a lot quicker.
Gamma rays is another useful type of radiation. They can be used for cancer treatment, but that's the weak rays. And now radium is used because it's quicker and safer, because the radiation from the radium can kill cells with death.
They also use radioactive in waste and stuff to break it down so they can get rid of it easily.
Carbon dating is another good use. It can be used for museums to find out the age of the dead.
They also use it in like photographic films so they get a clear picture.
Krypton dating is another one. It can be used to check lungs, and it's used in hospitals.
They also use ultraviolet light in saunas.
That's it.
I'll talk about background radiation. Background radiation is radiation that is always present in the environment. By far, a greater proportion, 87% of it, is emitted from natural sources. Alpha and beta particles of gamma radiation are radiated by the traces of radioactive minerals that occur naturally in the environment and even in the human body. By radioactive gases such as radon and fluorine, which are found in soil and may seep upwards into buildings.
Radiation from space also contributes to the background level. This is known as cosmic radiation. Cosmic radiation is when streams of high-energy particles from outer space, consisting of protons, alpha particles, and light nuclei, respond atomic nuclei in the Earth's atmosphere and produce secondary nuclear particles, mesons such as pions and muons that share in the Earth. Those of low energy seem to be galactic in origin, and those of high energy are galactic origin. The galactic partroids may come from supernova explosions or pulses. At higher energies, other sources are necessary, possibly the giant jets of gas which are emitted from some galaxies.
Remaining 13% background radiation is almost entirely medical in origin. Less than 0.1% of background radiation can be traced to the normal operation of nuclear power stations. Because background radiation increases the count rate of time during any experimental work on radioactive materials, background count rate is usually subtracted from any date of 10.
Our talk is based on background radiation. Background radiation is all around us. It comes from natural sources like granite. Other toxic gamma rays, radon gases in rocks, soils, groundwater and building materials, and radioactive potassium in human tissues. Over the years, background levels of natural radiation exposure from all sources has increased, although man-made has remained the same. Radon is the main source of human exposure to ionizing radiation. It can be found in the home and is a naturally occurring radioactive gas. It is produced by radium decay in rocks and soils. If there are large amounts of radon, you can later develop lung cancer.
This table shows the sources of human exposure to natural and artificial gases in the population. As you can see, the USA produces much more radon than the UK. In fact, that 20,000 homes, 25% contain a higher amount of radon than they should. By looking at the table, you can see that the natural sources such as radon, pollen and gamma rays all amount to a higher dosage than the artificial sources.
Radiation exposure is very dangerous and too much of it can damage. Like with the radon, it can cause illnesses such as lung cancer. We must not exceed more of this radiation as it may return later in life. Thank you.
We did a project on radiation can be harmful. A nuclear bomb releases radiation. This can cause serious long-term injuries, that is if people survive the heat and the blast of the explosion. People of all ages were injured on the 9th of August 1945 when the US dropped an atomic bomb on Nagasaki in Japan.
In an atomic bomb, chain reactions build up until they're out of control. The bomb explodes, giving out heat, violent shockwave and a burst of radiation. The earth is scorched for miles around, burning things, and the air is poisoned. All living things are killed. But this is not spotted for days and weeks.
It is dangerous to handle radioactive substances without protection. A small amount can lead to leukemia or cancer, but a large amount can kill within minutes.
In 1984, a US judge ruled that 10 people had suffered cancer because of government negligence concerning public exposure to fallout in the state. Radioactive fallout is caused by nuclear fission and activation of soil, air, water and other materials in the vicinity of the detonation.
Useful uses of radiation. Objects give out invisible light and heat energy called infrared. Like all forms of light, it travels in straight lines. The elements of an electric fire radiate heat. If you face the fire, heat energy will be absorbed by the part of your body facing the fire. This will make you feel warm. Your back will feel cold. Heating appliances are each designed to spread heat in different ways. An electric fire spreads heat mainly by radiation. A radiator is designed to spread heat by convection, but there is always some overlap between one system and another. In the radiator, for example, the metal conducts heat. If you put your hand very close to the radiator, you will feel radiated heat. The heat energy from the sun cannot reach the earth by conduction or convection currents, because neither of these ways of transferring heat is possible in the vacuum of space. So in the same way that a halogen bulb heats a saucepan, the earth is warmed up by infrared heat energy from the sun. The colour of the surface affects how much heat energy is absorbed. Dark-coloured clothes absorb heat better than light-coloured clothes. So in winter we tend to wear darker-coloured clothing. In summer, paler clothes are more popular because the lighter surface reflects more of the heat. Shiny or highly polished surfaces absorb the least heat of all because they reflect nearly all of the radiation that strikes them. The space shuttle has a highly reflective tile to reflect the heat as it passes through the Earth's atmosphere. An open fire or a simple electric fire can only heat a small part of the room by radiation. Convection is a much better way to heat living spaces, which is why radiators or electric convection heaters are used in modern homes.
Ionizing radiation has different penetrating properties. They are also important in the use of radioactive materials. Naturally occurring alpha rays are stopped by a few thicknesses of paper or a rubber glove. Beta rays are stopped by a few centimetres of glue. Gamma rays and X-rays depend on their energies, require thick shielding of a heavy material such as iron, lead or concrete.
Infrared radiation comes from everything, especially radiators and fire. Infrared radiation
radiation is produced from molecules that are vibrating rapidly. When something is red hot, some wavelengths are so short that the eye can see it. We can't see ultraviolet radiation, but it gives us a suntan. X-rays are produced by an X-ray tube. X-rays come out when fast-moving electrons bang into a metal target. Short wavelength X-rays penetrate lead. Long wavelength X-rays penetrate flesh but not bone, so you can only see the bones on the X-ray.
One use of radiation is in a greenhouse. It keeps plants warm. Short wavelength radiation from the sun passes easily through the glass of the greenhouse. It warms the plants inside. The warm plants also radiate heat, but the wavelengths are longer and don't pass so easily through the glass. The result of this is a warm greenhouse.
Well, we're going to talk about the dangers of radiation. Radiation can be very dangerous if it's not treated properly. People who work with it are in danger of getting a certain type of cancer, which is lung cancer, or they can get leukemia, or they can just kill you if you have loads of it.
Radiation is used in atom bombs. These bombs were first used in the month of August 1945 in the Japanese city of Hiroshima. The bombs were dropped by the Americans and it wiped out the whole city, killing many men, women and children. It destroyed everything and it changes the climate. Also, it deforms people and forms their up-and-coming generations.
If radiation is exposed to people for a long time, it can make them die, or it can harm their children.
Overall, radiation can be very dangerous if it's not treated properly, but if it is, it can be very helpful.
This presentation is about the dangers of radiation. We have chosen to look at Chernobyl. Chernobyl is a town in north-central Ukraine, just 20 kilometres from the nuclear power plant. On April 26, 1986, the power plant blew up, causing the world's worst known reactor disaster to date. Some of the radiation spread across northern Europe and into Great Britain. More than 135,000 Soviet citizens were killed. Lots of regions remained unoccupied a year later, and a few areas are still unoccupied now. This is a picture of the nuclear power plant, and these are the radiation victims.
Our focus on background radiation. Background radiation in astronomy is a low-temperature microwave radiation that arrives to Earth from all directions of space. It's named this because it forms the background to all the radio sources that have ever been detected. It was first detected in the USA by astronomers Arno Pizaius and Robert Wilson. Wilson found it in 1965 while he was working at Bell Telephone Laboratories in New Jersey.
Cosmic background radiation was first brought about in 1948, part of the Big Bang theory of the origin of the universe, cosmology. According to the theory, cosmic radiation is the remains of extremely hot conditions found in the early stages of the Big Bang.
Background radiation is quite smooth. For all instruments apart from the most sensitive, the characteristics of background radiation are the same, no matter which direction the instrument is pointing in. However, it is shown in the early 1990s from data from the Cosmic Background Explorer code that background radiation is not entirely uniform. It is believed that the small ripples in the background radiation are left over from non-uniform that were present in the universe soon after the Big Bang. These non-uniform regions in the early universe may have served as the seeds for the early galaxy formation.
This picture shows background radiation. On the picture it shows the colours corresponding to radiation temperatures. The red is the hottest part and the dark blue the coolest. The pink represents emission from the Milky Way. The variation in temperature was the result of different densities in the early universe.
The end. Hello and welcome to Open University on Channel 2. I am Luke and this is
Safe.
we are your professors for today. Today we are looking at the good points of nuclear physics and atomic power.
Okay.
On that first point, it's safe.
There are many power stations, nuclear power stations today. The first reactor was built in 1944, Hanford in Washington.
They were used to build nuclear weapons and nuclear materials. It is also used in X-rays. They were discovered in 1895 by accident in the German lab. He was studying cathode rays in a high voltage tube.
Radiation is also used in radios. For example, in the early 30s and 40s, in comparison to the 1990s style radios used cosmic rays and electrons to transmit messages. It is a very useful part of modern day life. Other uses and notes to take down in your logbook. Altimeter beams radiation down to see how high a plane is and how high the ocean is. Infrared is used in cooking and heating. That is also used in defense systems such as alarms for your everyday house. They are also used for chemotherapy, which is a very important use of cancer research.
And also ultraviolet for sunbeds and
That is-
tans.
That is all from Luke and
Save today.
on this week's version of Open University on Channel 2. Catch us next week, same time, same place.
What?
Year 9 talks on radiation. Our talk is about radiation and its uses. Radioactivity has helped man over the last 25 years, has helped in the diagnosis of disease and enabled industry to make better and cheaper products. Radiation can be used for many things. It can be used in brain scans and for sterilisation. Dentists and surgeons use it to boil their instruments, and penicillin is packaged in it.
My talk's on dangers of radiation. Radiation damage to humans can be very serious. One of the most common types of radiation damage to humans is due to their ultraviolet rays and sun rays. These lead to sunburn and tanning of the skin. Damage is usually of little importance. High levels of radiation covering the whole body disrupt the blood cells so seriously that life cannot be maintained. For a whole body doses in excess of 5.0 SV, death is likely. Even a whole body dose of 1.0 SV can cause radiation sickness of a very serious, although non-fatal nature. Whole body doses in a range of 0.30 SV and above cause blood abnormalities. Even very low radiation doses reaching the reproductive regions are potentially dangerous. The DNA molecules in our body that carry reproductive information can be disrupted by a single radiation impact. If enough of these molecules are damaged, defective reproductive information will be furnished to the fetus as it develops. As a result of birth, abnormalities will occur. In addition to causing birth abnormalities, low levels of radiation present two other hazards. First, there appears to be a delayed cancer effect. Although cancer may not appear at once, low levels of radiation may cause it to develop many years, growing rapidly. Many cells mutations. Second, a child is particularly vulnerable to radiation.
Because the child is growing rapidly, any cells mutations caused by radiation may have serious consequences.
Our talks on background radiation. Radiation was first used for X-rays in 1895 by W.C. Roentgen, and this turn led to the discovery of radioactivity by Becquerel in 1896. On the 8th of November 1895, Roentgen enclosed a discharge box in a tube with a bit of thin black cardboard in a darkened room with a box made screen of platinum cyanide, which would be used for the X-ray. But in 1912, they finally proved that X-rays were electromagnetic radiation. In other words, they resemble light that have a much higher frequency. Nobody really knows why they are called X-rays, but some say that it's something to do with the algebraic letter X. X-rays work because they could travel through flesh, but not so easily through bone. To find a lot of radioactivity, people would use a Geiger ruler. This would work by counting the electric pulses received from the Geiger tube. The tube generates such a pulse whenever a radioactive particles enters it, as it also does with a gamma ray. There are three different types of radioactivity. Alpha ray, whose large numbers of iron also dense tracks in the cloud chamber, operates many other things. Beta radiation produces ions, but not as many of the alpha particles discharged on electroscope, but less easily than alpha particles. It also produces tracks in the cloud chamber, but these are less dense than alpha particle tracks. The third and last radiation produces iron, but fewer than alpha, and beta radiation does not appear to discharge on electroscope, nor operate at a spark count that travels in straight line.
Radioactivity is a property possessed by some elements like uranium, are spontaneously emitting alpha or beta rays, and sometimes gamma rays by disintegration of the nuclear atom. It was discovered in 1896 by the French physicist Henry Becquerel, when he saw that the element uranium can break a photographic plate, although separated from it by glass or black paste. In 1898, the French chemists Marie Curie and Pierre Curie found out that radioactivity is associated with atoms. Marie Curie also found out that element thorium is radioactive. Radioactivity was soon recognized as a new concentration source of energy that had been known before. 1 gram of radium gives off about 100 calories of energy every hour. Alpha, beta and gamma radiations are all from nuclei. Alpha particles penetrate into aluminium only a few thousandths of a centimetre. Beta particles are nearly 100 times more penetrating. At the time of the discovery of radioactivity, physicists believed that the atom was the ultimate invisible building block of matter. Thorium-234 emits beta particles, which are electrons. Beta emissions is accomplished by the transformation of a neutron into a proton, resulting in a nuclear charge of 1 unit.
The breaking up of unstable atoms is called radioactive decay. It happens all around you all the time. If you use a GM tube to detect this, read background. In radiation decay, you can't tell which atom will break up next, as it is completely random.
Thank you. My name's Lee, this is Keith, and this is Craig, and this is our talk about radiation. Some of the uses of radiation are: gamma rays can be used to keep fruit like strawberries fresh, shaping the thickness of tiles by having a beta source on one side and a detector on the other side. If the detector picks up too much radiation, then it is being made too thin. Gamma rays can be used to take X-ray type photographs of welded metal joints, and gamma rays can also kill cancer cells in one small area of the body. Lungs can be checked using a radioactive tracer. The flow of the gas in the lungs can be watched on a TV screen. Radioactivity can be used for X-rays. This was invented by W.C. Roentgen, who observed the light production when Hole tube ray struck the glass walls of the discharge tube. In dense
luminous is made if the tube is coated in zinc sulphate. In 1895, Roentgen put a discharge tube in a box with thin black cardboard in a dark room. Next door to the box lays a screen of platinum. He noticed that the screen showed a brilliant light when the tube was in operation.
Another use of radioactivity is nuclear bombs. Nuclear bombs were dropped on Japan in the Hiroshima War. A nuclear explosion wiped out some of Japan when a fire explosion stretched over and ruined buildings and caused a lot of deaths. The radiation from this explosion reaches around other parts of the world. One example of this is when the Chernobyl power station exploded in USSR and the radiation killed English and Welsh sheep. Nuclear bombs aren't used very often, but when they are, there is always great danger. Nuclear bombs are usually used by the Americans.
And that's our talk complete.
We're doing a talk on the good uses of radiation.
Radiation is used in a type of medicine called X-rays. X-rays help us to see pictures of the inside of our body, telling us if we are healthy or if our brain's broken.
Sterilisation. This is another sort of medicine. It is used for killing most forms of organisms, including bacteria.
Agriculture. It is used to increase the plants we're speeding up.
Carbon dating. This is when archaeologists have an interest in carbon dating. The carbon soon combines with oxygen to form carbon dioxide.
Industry. This is to measure the amount of wear in moving parts of an engine, e.g. a radioactive piston ring.
Radiation is used is a good thing because if we didn't have radiation we wouldn't have the things like X-rays in agriculture.
Switch off. I'm doing a talk like everyone else. My name is Natalie. I'm doing radiation effects biological. Radiation effects biological effects observed when ionising radiation interacts with living tissue by transferring energy to molecules of cellular matter. Cellular function may be temporarily or permanently impaired as a result of such interaction, or a cell may be destroyed. Severity of the injury depends on the type of radiation that absorbed dose, the rate at which the dose was absorbed, and the radiosensitivity of the tissues involved. The effects are the same whether from a radiation source outside the body or from material within. The biological effects of a large dose of radiation delivered rapidly differ greatly from those of the same dose delivered slowly. The effects of rapidity induce cell death, and they become appeared within hours, days or weeks. Protracted exposure is better tolerated because some of the damage is repaired by the exposure continues, even if the total dose is relatively high. If the dose is sufficient to cause accurate clinical effects, however, repair is less likely and may be slow. Even if it does occur, exposure to doses radiation too low to destroy cells can induce cellular changes and may be detectable clinically after some years.
Our talk is on radiation protection. To produce and maintain an environment both at work and the outside where the level of ionising radiation is safe for human beings.
Sources of ionising radiation. Natural background, 87%. Medical irradiation, 11.5%. Radioactive fallout, 0.5%. Occupational exposure, 0.4%. Radioactive waste disposal, 0.1%. Miscellaneous, 0.5%. Natural radiation has always existed in the environment in the form of cosmic rays, radiation from granite and other rock and other sources.
Radiation protection procedures can do nothing to reduce this radiation, which therefore constitutes a lower limit to the radiation doses received by the population at large.
It is important to determine the levels of risk to the population. Once this has been ascertained, approximate maximum permissible doses can be set, which, for instance, will protect workers with radiation from early death and disfigurement.
The absorbed dose. The energy absorbed by the medium is the absorbed dose. Absorbed dose. The radiation, EM, where E is the energy absorbed by the medium due to a beam of ionising radiation in a small mass, M. The unit of absorbed dose is the gray, GY, where 1 gray equals 1 joule per kilogram. The former unit was the rad minus 1, was gray equals 100 rads. The unit used to measure the overall biological effect of different ionising radiation is called the dose equivalent and is measured in sieverts, SV. The former unit was the rem, where 1 sievert equals 100 rem.
The energies absorbed in a medium due to alpha and beta particles, protons, neutrons, X-rays and gamma rays are measured in grays. It cannot be interfered through that the absorbed dose for a different medium will be the same to be the same. They must both absorb the same total energy from the beam per unit mass. However, the effects in a biological sample do not solely depend upon the absorbed dose. The type of ionising radiation and the absorbed dose rate are also important. E.g., particles have a greater biological effect than X-rays.
This is a representation of radioactive decay.
My talk is on the effects of radiation. The atomic bomb is a nuclear weapon, and the devastating explosion caused as such in the bombing of Japan, with devastating effects, millions killed. Those who survived suffered from radiation burns.